So these are going to be the molecular orbital diagrams for some transition metal complexes. I did chromium with 6 hydrogens around it in an octahedral complex. So this would be called an octahedral crystal field. And that word crystal field is something that you should know. So go ahead and write that down. Crystal field theory. So crystal field theory puts a particular D block element in a particular type of environment. And so they could be like an octahedral crystal field or a tetrahedral crystal field. And even though it's not a crystal, it's a single atom surrounded by 6 things, that would be the way that atom would behave in a crystal that had 6 nearest neighbors. Or in a crystal with 4 nearest neighbors, that would be a tetrahedral crystal field. So this does apply to solids where you have D block elements in solids. But for simplicity, we just have a gas phase molecule. We have chromium hexahydrate. So we have 6 hydrogens around it. Now, why did I pick hydrogen? Well, because it only has a 1s orbital. Okay, so it's complicated enough when the ligands that are around the chromium only have 1 orbital. Can you imagine, after going through this, I'll ask you, can you imagine to add in p orbitals on the ligands? And so it could be really, really confusing. So these are the types of crystal fields that we're going to talk about, the octahedral complex and the tetrahedral complex. And in most of the textbooks, they show this splitting. You have 5 equal d orbitals. And then in an octahedral field, it shows that they split with 2 up and 3 down. It really kind of depends upon how many unpaired electrons it has. Sometimes it can split 3 up and 2 down. And then the tetrahedral complexes typically split this way, depending on the number of electrons. And you can have a high spin or a low spin situation. So anyway, this is how the d orbitals are going to split, but this is the simplest sketch, but this is what you see in the textbooks. We're going to go into Gaussian and calculate the splittings. And so we'll actually get the full energy diagram of these complexes. And you can see there's places where it's really simple and then places where it gets crazy complex. And so I've illustrated the orbitals so that you can see the shapes of the orbitals. Okay, so this is the transition metal molecular orbitals in a chromium with 6 hydrogens around it. So this is just showing some of the orbitals. And here's the typical way you would draw the coordinate system. So this is something that I would definitely test you on right here. So you should be able to draw a octahedral coordinate system. Now there's 2 ways to draw it with the coordinate system, but this is the one that's being used for all of these orbitals. So you see how here's the chromium atom in the middle, and then you have the hydrogens coming out, and these x and y axes follow 2 of the hydrogen bonds, the chromium hydrogen bonds. Okay, so they go out towards the corners. Often I see it like this too. You draw the square, you draw the stick. So that's what's being shown as a tetrahedral complex. Okay, I'm sorry, octahedral complex. And sometimes people draw the coordinate system like this, where it comes out the sides of the square. So that would be x, y, and z. But in terms of the pictures today, it's using this one up here. Is everybody clear on that? That's the coordinate system. Can you see the octahedral thing here? That's another thing that you need to be good at, is to look at this octahedral complex and know that there's a atom at all 4 corners of the square, or ligand, like it could be water, it could be something in solution, an ammonia molecule, and down here at the bottom and the top. So you have sort of the poles and the equator. There's 6 things bonded on here, but it's called an octahedron. So where does the 8 come from, octa? If there's only 6 atoms, how do we get to 8? What's 8? Do anybody play dice, Dungeons and Dragons or anything? What if I were to go ahead and draw vertices on here, what would I end up with? I'm going to go back in the back with a dash line. What if I put numbers on these faces? 1, 2, 3, 4. Do you see the octa now? It's the faces. This is a D8 dice, right? And so that D8 is an octahedron. And it needs to be, you know, a real octahedron, because then all 8 faces are the same size and it's equal. You know, if it's elongated or whatever, then it may not be perfectly equal. But so the octahedron has 8 faces, but there's only 6 vertices, and those 6 vertices would be where the atoms are, or the molecules in an octahedral complex. Okay, so that's just the basics of the octahedral field. So let's put this into Gaussian. Here's all of the orbitals that we get out of Gaussian. So here's the energy level diagram. Look at the energies. I mean, it's crazy. This was really tedious. I hope you appreciate that in making all these pictures. So right here, with this, where it splits from negative to positive, that's right here. That's where the occupied and unoccupied orbitals split. So this is the highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital. Okay. And so all of these with positive energies are unoccupied. They don't have electrons in them. All the ones below that have negative energies have electrons in them. Is everybody fine with that? Look how low they go. Negative 574,000 kilojoules per mole. That's the energy holding those 1s electrons on the chromium. That's really low energy. It takes a lot of energy to pull that 1s electron away from chromium because it has 24 protons. So those 2 electrons in the 1s orbital are really close to 24 protons. So it'd be really hard to pull them away from something that's that attractive. Okay, so let's get into the pictures. So here's the full MO diagram with the energy levels put to scale, okay? And so we're looking down here, what do we see? Down at negative 578,000 kilojoules per mole, we have the chromium 1s, okay? And so that's all we would see. Let's zoom in on this part. Let's go into plus or minus 100,000, and this is what we see. So now we're able to see the N equals 2 shell, the chromium 2s and 2p's. Do you see how we say that those core electrons don't participate in bonding? And now you can really see it. That's negative 60,000 kilojoules per mole. So that's so deep in the chromium area, it doesn't even know there's hydrogens out there. Because energy, this negative energy, that is Coulombic attraction. So that's another way of saying how close those electrons are to the nucleus. The reason that they have such a low energy is because they're really close to the nucleus. What about the 3 shell? Do you think it participates in bonding? Let's look at the chromium. That's the previous shell, and it's full through argon. And so whenever those shells are full, they're core shells. And so they're not valence electrons. So let's zoom in here, plus or minus 10,000. And here are the 3p's. And notice that they are unperturbed. It looks like an S and 3p's. If they don't move around, they're probably not bonding. So even the N equals 3 shell in chromium is not bonding. It doesn't even know the hydrogens are there. So it's this upper part that's the valence band where you have the bonding. And so here, notice how it's hard to recognize an S or a P or anything like that. There's no 5 across, so the D, the 5 equal orbitals for the D shell are scrambled up and down. So that's the bonding part. So at this point, you can pick up your pen and say, the core electrons do not participate in bonding. Just to reinforce that, core electrons do not participate in bonding. And for the chromium, that's up through the 3p. So 1s, the 2s, 2p, 3s, 3p, none of those participate in the bonding. So for chromium, we just have the 4s and the 3ds. Those are the valence. The 4s and 3ds are the valence orbitals. Okay, so now let's look at the pictures. Oh, by the way, this was kind of cool. I got this email from this fellow in Germany studying in Munich, and I just had to show off. Okay, he says he's been taking online courses on spectroscopy from MIT and UC Irvine, but he said my lectures have provided with better imagination, information, and satisfaction than the other online courses. So that's part of why I put my lectures on YouTube, because it's great. So he asked for the slides. I sent him the PDFs. So anyway, that was nice. So this is a nice third-party endorsement of what you're learning, so be encouraged. And he even caught a mistake in this lecture, so he really was following it along. So there was like an EG or an EU that was mistakenly labeled. Okay, so let's look at let's look at the pictures. Let's go ahead and go down to the 1S and show the picture. This is the picture. The 1S is so small that even on a ball and stick drawing, like you can put your pencils down and just look at the pictures, and I'll point out something interesting eventually. Okay, that 1S orbital is inside the ball. So even the little balls that they draw in Gaussian, that orbital is smaller than the ball. It's so close to the nucleus, okay? So then we go to the 2 shell, n equals 2 shell. Now we can see the orbital, the little 2s, is a little bit bigger than the ball. You see that it's red down here, okay? And then the 2 p's are right here. Look how tiny those little p orbitals are. They're so close to the nucleus, they're sucked in. That's why they don't bond with the hydrogens. They don't stretch out that far. Okay, and you can see the X, Y, and Z. All right. Let's go to the n equals 3 shell. Okay, now look how big the 3s is. It almost touches the hydrogens. Okay, if it went past the hydrogens, it would participate in the bonding. But it gets close, but it's just going to 0. That's the 99%. I think it's probably like ISO value of 0.01 or 0.001. So it's either the 99% or the 99.9% surface that I drew. So 99% of that 3s orbital is inside that surface, that red surface. So 1% or less could interact with the hydrogens. And then same with the p orbitals. They taper off right at that p orbital. I mean, right at the end where the hydrogen is. So they don't really have a chance to bond with those hydrogens. So again, core electrons don't participate in bonding, only the valence band. So now that we have the valence shell bonding molecular orbitals, and this is where it gets crazy complicated. But my goal in this is to do 2 things. One, to kind of show you this little shorthand that I'm using, because it'll help us going forward. And then 2, to just give you an appreciation for how these orbitals mix together. Okay. So here the easiest one is the 4s shell on the chromium in phase with all of the hydrogens. So when it's red, the hydrogens are red, and so it just absorbs all the hydrogens, and they're in phase. So when the hydrogens blink green, they shrink down. So does the 4s on the chromium. So it's in phase with those hydrogens. And since there's no node that breaks the bond, we would call this a bonding orbital. Notice how different this is than local bond theory, which would put 2 electrons between the chromium and a hydrogen. And this is 2 electrons going around all 6 hydrogens. So there's 2 electrons in this molecular orbital, and it's bonding, but which one is it bonding with? It's not a local bond. It's a molecular orbital. So it's contributing to the bonding of the whole molecule. Okay. And then as far as the designation, I don't know in your notes if you can see that, but you can hopefully see it on the screen. I have the 4s here, and I have a plus 6 1s. So my designation is saying that the 4s orbital on chromium is in phase with 6 of the 1s orbitals. So the plus means it's in phase with them. So it's a bonding arrangement. If there's a plus, then I mean it's in phase. That means they're bonding with each other, and so that's what my designation is trying to say. Okay, let's look at the next one. Let's go over here to the 2DZ. Actually, yeah, it's the 3D orbital that is designated as 2 times the z squared minus x squared minus y squared. Okay, and then I have plus 6 1s. So it's saying that it's in phase with 6 of the hydrogens. Can you see how this was the little donut orbital? You know, the d orbital with the donut in the middle, the toroid. and it's in phase with those hydrogens, and so it just absorbs them. So there's no node between the hydrogen and the chromium. So this is bonding also for all 6. So all 6 chromium-hydrogen bonds are strengthened by this molecular orbital because there's no node, no node that breaks those bonds. And now this one is just the 3D orbital, which is designated by x squared minus y squared. So again, this might be the x-axis here. This is the x-axis. And the y-axis is out of like a different color than the x. So that's why it's x squared minus y squared. It's x squared because it's the same on the negative x and the positive x. So if I square the x-axis, it's positive in both directions. And so this is the same phase in both directions on x, but a different phase than y. So that's why there's a negative sign between them. And then it's in phase with 4 of the 1s's. And so on that designation, I put a plus 4 1s, just to show that it's strengthening the bonding of 4 of those hydrogens. Any questions on the pictures here? The symmetry of these orbitals was Eg, and then when it is in phase with those hydrogens, it still has the same symmetry. So these are Eg, that's a doubly degenerate. So in like if we were doing the Boltzmann distribution, G, well, that's probably going to be confusing. Anyway, the degeneracy term for the Boltzmann distribution would equal 2. Okay. And then for this one, the degeneracy equals 3. And that's something you should notice. So like in these MO diagrams, when you have 3 orbitals together, then that has a degeneracy of 3. When you have 2 orbitals together, it's a degeneracy of 2. Okay, let's look at these interactions with the p orbitals, the 4 p orbitals. So notice we have on chromium, the chromium row, we have those 4 p orbitals that are not populated. But when they mix in with these hydrogens and so on, we're bringing in 6 more electrons from the hydrogens, and the energy levels are moving around, and those 4 p orbitals showed up in this energy level diagram. Okay, and so here they are. It's triply degenerate, so it's a T. T1U is the in the character table for X, Y, and Z. It's T1U is the Millikan notation, and then I have it as plus 2 of the 1s orbitals. So because it's plus 2, it means it's in phase with only 2 of them, and so that's helping the bonding of two chromium hydrogen bonds for each one of these. So got 1/6. Yeah, okay, so we have 2 electrons in each of these molecular orbitals. Okay, and we have 6 bonding molecular orbitals. And so 2 electrons, and then times 6, we end up with 6 bonds. If a bond requires 2 electrons. So we still get the same answer of 6 electrons needed. I'm sorry, 2, 4, 6, 8, 10, 12. 12 electrons needed for 6 bonds. But notice it's not local bonds. We don't have 2 electrons between the chromium and the hydrogen on those, times 6, right? That's how we would draw the Lewis dot structure. We would have 6 single bonds with 2 electrons each. This is crazy complicated. But we still end up with the same bond order. We have 6 bonds here. So these are the molecular orbitals that hold that thing together. So that's pretty fun. Okay, let's look at some of the unoccupied orbitals. So this would be the, let's see, this would appear to be the 3D XZ, XY, and YZ. So these orbitals are not what I would call non-bonding, really. Because notice they don't have any interaction with the hydrogens. They go between the hydrogens in all 3 cases. And so they stay triply degenerate, and they pretty much stay where they are in terms of energy. So it was these other d orbitals here that dropped. If these were 5 degenerate orbitals, when we interacted with those hydrogens, these dropped in energy, and these pretty much stayed where they are. So that's that d orbital splitting, where 2 dropped and 3 stayed where they were. And then this one would be the antibonding orbital using the d. So it's this same orbital, but notice how it's a -6. I went ahead and changed this to 6 1s's because it really is interacting with 6. I don't know why I had a 2 there. So you scratch out the 2 and put a 6. And I put a plus sign to show that it was in phase with all of them. And so up here I have a minus sign to show it's out of phase. I don't know if you can see it. I can see it. Inside there, you see that little squished d orbital? It's got the 2 poles are green, and then the little donut around it is red, and the little donut's being squished by these hydrogens, and they're out of phase with all of the hydrogens. And so that again is going to be an antibonding arrangement. So that's got nodes that break the bond. So there's 6 nodes that break all 6 bonds here. And it's a good thing that doesn't have electrons in it, because that would weaken the bonds. Okay, and here's the other one. You can see that tiny little d x squared minus y squared here in the middle, and it's out of phase with 4 hydrogens. So the negative sign means it's out of phase with the 4 hydrogens. Okay. And so let's look at the p antibonding. So the 4p bonding ones are down here at the bottom. Up here are the antibonding ones. So it's really kind of a strange thing. This p orbital, the 4p orbital, is really squished like a pancake because of those hydrogens on the top and the bottom. Okay. And then this one, front and back, the x-axis, and then the y-axis. So do you see how that's the 4p out of phase with 2 of the hydrogens? There on the end, there's a node that cuts the bond. So those would be antibonding. And then let's look at the 4s bonding and antibonding. So the 4s is the easiest one to draw. You should probably be able to draw the interaction of an s orbital with as many hydrogen s orbitals as you can put on a molecule. I mean, essentially the lowest energy orbital in the bonding arrangement would be no nodes. Okay, and the one that's the highest energy would be the one with the most nodes. And so here is that 4s orbital out of phase with all 6 hydrogens, and so it's been squished into kind of like a little cube with 6 faces, because there's a node that breaks the bond for each one of those. So if we were to add enough electrons in here to populate all those antibonding orbitals, then this molecule would fall apart. Okay. And so let's talk about the D to D transitions. We talk about D to D transitions being the source of the colors in these transition metal crystals or in solution. And so let's look to see if those are populated or if those are allowed. So this is a part of the course where you could be tested on this in terms of the direct products for all of these. And so if you've got 2 orbitals that are EG, and you've got 3 orbitals that are T2G, right, you can set up the transition dipole moment integral with light to see if it's allowed. Right, so this should look familiar. And so let's do that. Are D to D transitions allowed? Well, here's the setup. The T2G is at the top, so it's on the left. The EG is down at the bottom, so it should be on the right. And the T1U is light. So light is T1U. I can put that over here. Where do we get those? We go to the octahedral character table. And we look over on the right-hand side and we find that, XYZ would be light, so that you come across that row's T1U. We're given T2G and EG in the problem, and so we would be able to fill this out. So let's go through this. Now, there's a if we take the T1U times the EG, we end up with this piece right here. Okay, so that's this first one. And this next one, it's T2G times T1U, gives you this top row of things. Okay, so this one, let's see, do I do the arrows? No. So this top one is the first pairing. So that's the first group. And then when I take T2G times the T2U, I get the bottom group. But notice how they're all U's. And so this is going to be 0. And in fact, this was a lot easier than we needed to make it, than we made it. Because we could just look at that and see, anytime we have an odd number of U's, we know it's going to be not allowed. Because G times U is U, and then G times U is U, and so it's going to be U at the end. And we know that can't be top row. So top row is always something G, like A1G or AG. Okay, so that one was easy, actually, just looking at the U's and the G's. Let's look at this one. So let's look at the HOMO to LUMO, this highest occupied molecular orbital, and the LUMO, the lowest unoccupied molecular orbital. So is that one allowed? So here's our symmetry setup, and already it's possible, right? We see 2 U's. So U times U is G, G times G is G, so we're good, at least for the GU symmetry. So it could possibly be allowed. And so this one I color-coded. So we did the T1U times T1U, and we get this whole group. So we did this one first, and that gives us this. And then we do them one term at a time. So I color-coded it. This one is the green one. T2G times A1G, we get anything times A1G is itself, okay? And then T2G times EG gives the next 2, the T1G and T2G. Then the light blue ones are given next. And then we have this last one, T2G times T2G. And anything times itself will give you an element that's top row. So even if you can't do all of this, let's say for whatever reason, you can't find the correct direct product table or can't figure that out, the G's and U's are going to give you G's. And that, if you were to get this far, then you would know that T2G times T2G is going to give you something with the A1G, and it will be not equal to 0. So it will be allowed. So this is a crazy integral. Remember, these brackets are necessary because they tell the reader that you're doing an integration over all space. And these symmetries are the symmetries of the waves and how they interact with light. So this is a crazy long integral result with lots of terms added together. And all we care about is one of those terms going to be non-zero. And so the integral over all space of an even function is non-zero, and A1G is even. So therefore, the HOMO to LUMO is allowed. So we can get this 4P to 3D transition to occur with light. And that's going to give this a really strong color. If our energies were accurate, we could predict the color of this substance, okay? I don't remember what basis set I used for this calculation, but this gap is 1,000 kilojoules per mole. I think that's too high for the visible region, but that's just because I didn't give it the biggest basis set. Okay, so the coordination complexes, this is just showing you some pictures of this applied with water. So it doesn't have to be hydrogen atoms. It can be any kind of thing. So if you put this copper complex into water, these are some of the molecular orbitals. And you see how the water, it's interacting with the P orbitals, the PZ orbitals on the oxygen that are in phase with the hydrogens. And so you can do the same thing. It just gets a little more complicated when you have the hydrogens on the oxygens. But this is the same kind of stuff that happens when you put an ion in water, is these d orbitals will mix with the orbitals on the ligands. Okay, let's look at the tetrahedral complex. Did you feel okay with the dz orbitals and the dxy orbitals and the hydrogens? Were you able to see some of those pictures? And give me some kind of feedback on that. Okay, there was a lot of strange little pictures, but at least they were understandable. I could see the d orbitals inside some of those pictures. The tetrahedral complex is crazy. Okay, so this one, I just would love to see if you can see what's in there, because it's really bizarre. First of all, the tetrahedron we draw typically like this with, say, methane, right? So if you were to draw a tetrahedron, if I would say, draw me a tetrahedral molecule, is this how you would draw it? Most likely. Okay, but this is a really, I don't want to say it. If you draw it this way, where do you put the z-axis, right? We've always said the z-axis is along the highest order symmetry axis. And methane has some C3 axes and some C2 axes, but it also has an S4 axis. And that z-axis is actually going along the S4. Now, what on earth do we do with that? What we do is we draw a cube. Okay, so can you draw a cube? Draw a cube with a square. So you start with a square like this, okay? Then you start giving it some depth. Go back into space like this. So practice drawing your cubes. Trust me, it'll help you when you get to inorganic, if you learn how to draw a cube, okay? And in the back, we could draw the little dashed lines. Okay. So that's my cube. And we put the carbon in the middle. So we put a little carbon in that tiny little box that's inside. So you see the cube has kind of a tiny little box inside. We put the carbon right there. And the z-axis comes out of the top of that cube. And the x-axis comes out of the face of the cube, out of that face, and the y-axis comes out of this face. Okay? Now, where do the hydrogens go? They go on opposite corners of the cube. So we're going to put a hydrogen here, and in the back corner, and in the front left corner, and in the back right corner. So you see it's a tetrahedron, but it's sitting on two of the hydrogens. So that's a different way to make a tetrahedron. It's not as easy to see until you learn, and then you look at it, you're like, oh yeah, I see it, but first time you see that, you may not say, oh yeah, that definitely is a tetrahedron. Okay. So, and if you were to, join all the hydrogens, you'd have four faces, and that's where the tetra comes from. And so if you're, again, a gamer, you had a four-sided die, it's probably a tetrahedron. Okay. And so that's what's being drawn here. We're looking right down one of the faces, and so this cube, we're looking right down. I think it's the z-axis that we're looking down. And so then the x, y, and z orbitals and the x, y, and z light are T2. The x, z, y, z, x, y, d orbitals are T2. The other two d orbitals are E, and then the s orbitals are A1. We don't have g's and u's in a tetrahedral molecule. Okay, so let's jump in. Now, this is so bizarre. This is where you have some of the things that break your brain. Okay. Here's the cube that I was drawing. So let me draw this is the front face of the cube. And then it goes back to that hydrogen. This goes back to nothing. This goes back to that hydrogen. Can you see it now? That's the cube. Here's the dashed lines that we drew. And the carbon is in the middle. So there's our cube and our tetrahedron with the hydrogens on opposite corners. Okay. And on that chromium, we have a p orbital that's going up and down, and it's in phase with the hydrogens, and it's mixed together with this 3dxy. So we've got a lot of things mixed together, and you could argue with me on whether it should be +4 hydrogens or +2 and -2. I'm just trying to show that two of the hydrogens are one color and the other two are a different color. So that's why I have the hydrogens split in 2+ and 2-. So that's a really bizarre orbital, but we see a lot of these. So there's three ways you could put this together. You have the PZ, you have the PX, and the PY. So maybe the py is a little easier to see. So that's the py orbital on the chromium. It's the dxz orbital. So we have let's see, let's see. It's going to be the one that, well, I showed it earlier. I showed you how it mixes here. Okay. It's hard for me to draw that. And then the two hydrogens in phase without it, but out of phase with each other. So those are the three orbitals that are up here in the highest occupied molecular orbital. Now let's look at the non-bonding ones. So this would be the PZ DXYs. And look at those crazy kind of loopy things that loop together. So those are the non-bonding ones. Again, that's why I said put your pencils down, because what are you gonna write down on these? They're just really strange pictures. Okay, and in fact, it took me some time to kind of chew on what was being used to make them. Like what atomic orbitals on titanium are being used to make these molecular orbitals. It wasn't easy to figure out. But what we can figure out is whether the HOMO to LUMO transitions are allowed. The non-bonding ones are easy because they're pure orbitals. The dx squared minus y squared, and then the dz squared minus x squared minus y squared. So that's a traditional d orbital. Notice it doesn't go towards any hydrogens, and so it just doesn't interact. So those are non-bonding orbitals. And then here's the antibonding 4s minus the 4-1s orbitals. Here's some other antibonding molecular orbitals. And so here's our energy level diagram. This is one that Gaussian produced. So it will produce the sort of triply degenerate, doubly degenerate groupings. We have the occupied orbitals with the electrons in them, the unoccupied orbitals without. These energies are in Hartrees. And one Hartree is equal to about 25 kilojoules per mole. Okay, so when it's like a tiny little difference of negative 0.4, it's 0.4 times 2,600 kilojoules per mole. So it's quite a bit of energy. So here's the triply degenerate highest occupied molecular orbital going to the triply degenerate LUMO. And so we have it again color coded. This first pairing gives us this group. And we have A1 coming out of that, but then we still have to multiply by T2. So that A1 is going to produce a T2. So don't get too excited by that A1. But over here we have a T2. So T2 times T2 is going to give us an A1. So here's the whole grouping of everything. Again, color-coded. That first term gives us T2. The second term gives us two terms that are T1 and T2. And then the T1 gives us the light blue terms, which is almost there, but it's a T2 times T1. Because those numbers are different, it gives us an A2. And then we have T2 times T2, which gives us that A1. So we do have an A1 in that group, so it's allowed. That integral is not equal to 0. And so the HOMO to LUMO transition is allowed in this tetrahedral complex. So are the D to D transitions allowed? Now these Ds are not occupied, but still, we talk about D to D transitions in transition metal complexes. So let's just do the symmetry on that. We have the T2 times T2 gives you that initial grouping, and then the E times A1, E times E, and there we have an A1. So anytime we have E times E or anything times itself, we get an A1. And so yes, that E times E gives us a term that when you integrate it over all space is going to be not equal to 0. So the D to D transitions are allowed in this molecule. So the only crystal field where the D to D transitions were not allowed was in the octahedral Okay, it so happened in this particular energy level diagram for the chromium hexahydrate, it was not the highest occupied molecular orbital, that was the p orbitals, and so that was an unallowed transition. And so I guess the bottom line is whenever you put these transition metals into solution, the interactions of those molecular orbitals really give us a lot of transitions in the visible region of the spectrum. So many of the organic molecules have transitions in the UV. The HOMO to LUMO gap is too far apart, so they're not very colored. We have to extend the pi cloud. So what are we doing? We're increasing the box length, which lowers the energies and brings those UV transitions down into the visible region to make an organic dye. But early on, looking at soil, you go to Palo Duro Canyon and look at the walls of the canyon, and you see purples and greens and blues, and not so much blue, but there's some, and a lot of red. And those are these transition metals that are in the different clay structures. And so, you know, you're going to decorate your cave back in the caveman days. You're going to go out and find some green clay and mix it up and paint that green clay on there or whatever. And so that's the earliest pigments we're using, these transition metals. And these are some of the great colors that we get. I mean, and they really they really depend upon the charge. Like this is chromate, dichromate, chromium. All three of these colors come from chromium. Why is that? It's because of the different energies and populations of these molecular orbitals. Here's manganate and permanganate. Here's iron 2 and iron 3. What a difference it makes just taking one more electron off. It shifts all of those orbitals and you get something that moves into the visible region. Here's cobalt, copper, nickel, etc. So all these metal complexes, they really do form a lot of great color compounds. When you get to inorganic, you'll actually study the changes in colors with different ligands. You'll put on things like cyanide groups, water, ammonia, and so on, and you'll look at the changes in these transitions. So you'll have a great weekend.